This question we had done, which of the following will have the most negative electron gain enthalpy and which the least negative? And for that, you need where these are placed. So quickly draw their positions whenever you get these type of questions on rough paper. Their positions you need to draw. Otherwise, there are fair chances that you can make mistakes. Electron gain enthalpy is most negative of chlorine. We know that. In the periodic table, it is chlorine which has the most negative electron gain enthalpy, even greater than fluorine due to very small size of fluorine. So obviously, out of these, chlorine will have most negative electron gain enthalpy and least negative. So if we move across the period, electron gain enthalpy, negative electron gain enthalpy actually increases. So it means phosphorus will have least electron gain enthalpy, negative electron gain enthalpy. Now, if there is any confusion, let me know. Quite a few students have confusion here. They get
Sir,
confused with negative sign. Negative sign just tells you that it is release of energy. That's it. Otherwise, negative does not mean that it is actually negative. Okay. So more negative electron gain enthalpy means energy is greater, but it is being released. More negative does not mean that it is less than the other one. So it is not the mathematical interpretation here. The interpretation is in chemistry. So in mathematics, suppose you say something is more negative on the number line, sorry, -1, -2 is more negative. So -2 is less than -1. But in chemistry, this is not the concept. In chemistry, more negative means more energy is being released. That's it. The negative sign just says that this energy is coming out of the atom, nothing else. Yes, any confusion?
sir,
Yes.
sir, can you please tell again that, sir, how phosphorus will have the least negative electron gain enthalpy?
Yes. So do you remember the trends we talked about? Trend is that electron gain enthalpy normally when we are talking about across the period, okay, the electron gain enthalpy becomes more negative.
And so across a group, it becomes less.
Yes. And across down the group, it becomes less negative. This is something you need to remember. And what was the reason? The reason was whether it is accepting the electron, then it is releasing the energy, or we need to provide the energy. So less negative sometimes means positive. Okay, so it can be more negative here. Say it can be. I'm talking about units -3, then less negative -2, then it can be +1. It can be +2 also. +2 is less negative. It is more positive. More positive means less negative. So first you need to understand these trends and you need to memorize. I'll show you the chart also, which is something you need to paste somewhere on your study table and memorize that chart.
Yes.
With that concept, if you see, phosphorus is out of these given ones. Okay, phosphorus, sulfur, chlorine. Phosphorus is towards left, most left. Okay? So it means here when we are moving towards right, it becomes more negative. It means here it will be least negative. This one will be most negative.
Okay, sir, I got it.
Now the next concept, and this one again slightly confusing, and students are confused between electronegativity and electron gain enthalpy because electron gain enthalpy we talk about that is negative energy, but these are entirely different concepts. Entirely different concepts. Okay, electronegativity is nothing but the tendency. Electronegativity is just tendency. to attract the shared electron pair towards itself. How we can understand it? So first the definition. It is just a qualitative measure of the ability or tendency of an atom in a chemical compound to attract the shared electron pair towards itself. So if there is one atom, another atom, the one which can pull with greater force is called more electronegative. Okay. So suppose this kid can pull with greater force, we will say that it is more electronegative. Now, keyword here written is qualitative. The difference between qualitative and quantitative is quantitative means you can have some value of it. You can measure it. Okay. Although we have some means of measuring electronegativity also. Okay. But difference between qualitative and quantitative means this is quantity. Quantity means you can count it, you can measure it. Okay? So this is something when we are talking about percentage, we are talking about grams, we are talking about numbers. These are quantities. So how much percentage, what is the ratio? Okay, these are quantitative analysis. Qualitative analysis is whether it is present or it is not present or it is comparative. Less than, greater than. We can't say exact value. We can say yes, no, or it is greater than, it is less than, as compared to something else. Then we say it is qualitative analysis. To
So the
understand
comparison.
comparison is qualitative and exact values are quantitative analysis. So in organic chemistry also, we will be talking about these two terms again, because in detail, we will be doing qualitative analysis and quantitative analysis of the elements present in organic compounds. So the same thing we will be talking about, same definition. Wherever we will talk about quantitative, we will say that how much carbon is present in this compound, how much nitrogen is present in this compound. So that will be quantitative analysis. Okay, how much carbon, or how much nitrogen in say C2H5NH2. That will be quantitative. But if we are talking about qualitative, we will say whether nitrogen is present in compound A. This will be qualitative analysis. We are not talking about how much, we are talking about whether it is present or not present. So same thing we need to understand here also. This is electronegativity is again qualitative measure, means as compared to the other one. So why I am saying it is more electronegative, because in these two, out of these two kits, this one can pull with a greater force. But suppose we have another person, okay, who comes in, or another kit, and he pulls even with greater force than this one. So that will be even more electronegative than this one. Then this will become less electronegative. Okay. So A will become less electronegative in that case. So this is just a qualitative measure. So unlike ionization enthalpy and electron gain enthalpy, it is not a measurable quantity. Ionization enthalpy, you can measure how much energy is required to remove an electron from the atom from its ground state. Okay, free gaseous ground state. Or electron gain enthalpy, how much energy will be required or released when an atom gains an electron in its free gaseous ground state. Remember,
Sir,
yes.
sir, you said that electronegativity can't be measured, sir, but can't it be measured on the basis of the valence electrons?
No, we can measure. There is one way on the basis of few scales. Obviously, uh, those scales are that we assigned some arbitrary value to fluorine, and then with as compared to that one, we can measure. But
Yes.
absolute value cannot be measured.
Okay, sir.
Ionization enthalpy will always be positive because you have to provide the energy to remove an electron. Okay? Electron gain enthalpy can be positive or negative. Okay? In some cases, to make an atom get an electron, you will have to force it. For example, Na plus, sorry, Na. This will not accept electron. There is no reason it should accept electron because it will be more unstable. So you will have to force an electron into it. So that will be positive. But if you inject an electron in chlorine, chlorine is willing to get an electron to obtain noble gas configuration of argon. So in that case, it will become more stable. Chloride ion is more stable. So it will release the energy. So electron gain enthalpy can be positive or negative. But electronegativity is not a measurable quantity. With respect to some Pauli's scale, for example, with reference value assigned to fluorine. So what Pauli did, Pauli assigned an electronegativity value of 4 to fluorine. Okay. And as compared to that, we have electronegativity values of other elements. Again, not very much in use, so not too many questions will be there. So however, a number of numerical scales of electronegativity of elements visualizing Pauling scale, Mulliken-Jaffe scale, Allred-Roschow scale have been developed.
Sir, do we have to note this?
No, 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 no. This is just for reference. This part is actually you can totally skip. This one you should know that what Pauling did, the first one. Okay? This. He assigned arbitrary value of 4 to fluorine, the element considered to have the greatest ability to attract electron. So fluorine is most electronegative element in the periodic table. So that's why this has been assigned a value of 4. With respect to this one, we have electronegativity value of others. Now don't get confused that I'm talking about electronegativity. So fluorine has highest electronegativity, not electron gain enthalpy. There is exception for electron gain enthalpy. In periodic table, the most negative electron gain enthalpy is of chlorine, not of fluorine due to exception. The electronegativity of any given element is not constant. It varies depending on the element to which it is bound. That's what I said. Suppose I have A and B bond. Okay. And here B is more electronegative. So suppose this is chlorine and carbon. Chlorine is on the right hand side. So it is more electronegative. So this will be slightly negative. This will acquire slightly positive charge. So chlorine will pull the electron cloud towards itself. This is called electron cloud. Shared electron pair is also termed as electron cloud. But suppose I get an electropositive element. Say I get magnesium connected to it. Now magnesium is highly electropositive element. In this case, carbon will become slightly electronegative. Magnesium will be electropositive. So it is always comparative in terms of electronegativity. You just need to understand this concept and one or two questions can appear from here. But if you understand what I'm saying, that it cannot be measured absolute value with absolute value, that's something you need to know. Though it is not a measurable quantity, it does provide a means of predicting the nature of force that holds a pair of atoms together, a relationship that we will explore later in chemical bonding. Yeah. Electronegativity generally increases across a period from left to right, say from lithium to fluorine, and decreases down the group, fluorine to acetate. Again, the trend is similar as per the more negative electron gain enthalpy. So it will increase across the period, decrease down the electronegativity. Means you will have most electropositive element here and most electronegative element here with this trend increasing towards right, decreasing towards bottom. Okay. Understand it if you're not able to understand. Suppose I am talking about one period. In this period, I will have least electronegative here. Within a period because it is increasing from left to right. So least to most. But again from top to bottom down the group, it decreases. So it is already least electronegative and it will further decrease and it will become most electropositive. So say here it is -4, from -4 to say -2, say, then 0, +1, +2, then from +2 to again +3, +4. Electronegativity is decreasing. So from minus to plus, it means most electronegative to most electropositive. Just try to retain these concepts when we do the questions. It will be clear you are able to apply these concepts or not at that place. The attraction between the outer valence electrons and the nucleus increases as the atomic radius decreases in period. The electronegativity also increases. How these are interrelated? Can you guess? We are saying that the force of attraction increases when we move across the period. Atomic radius decreases. Atomic radius also decreases. The electronegativity increases. What is electronegativity? Electronegativity is a tendency to attract the electron pair towards itself. When the shared electrons are there, in this case, the shared electrons are farthest away. Shared electrons bond length will be, say, another bond is here, another atom is here. The bond length will be here, this much length. It means the electrons will be away from this nucleus. Radius is large, but here radius is small in this case. If radius is small, another atom is here. So it means this electron pair is closer to the nucleus. So it is closer to nucleus, it will be able to attract it towards itself with greater force. So it is just the distance which is actually responsible, distance of the electron pair from the nucleus, which is responsible for electronegativity. We are moving from left to right. The distance of valence electron decreases from the nucleus. It means force of attraction increases. And that is by definition electronegativity. Electronegativity is the ability of an atom to attract paired electron pairs towards itself. So if its radius is small, its distance, nucleus distance from the shared electron pair is small, it will attract the electron pair with greater force, higher the electronegativity. These type of concepts, why I'm going into much details, because these type of concepts will be used in your competitive examinations more. And if you don't understand these concepts now, it is highly unlikely that you will be able to do it in crash course after 12th. Crash course can help only if you understand these concepts, at least 60, 70%, 80% of these concepts already. Then you will be able to apply.
Sir,
Yes.
sir, in this case of electronegativity, you just told that as we move across a period, the atomic radius decreases due to nuclear force of attraction. So, but then, what about the shielding effect for this case?
Hmm. Now, as I told you, in few cases, shielding effect prevails. In few cases, the force of attraction prevails. Okay.
Yes, sir.
Along with the exceptions I told you, due to the fully filled configuration and half filled configuration, those exceptions will be there. What I am talking about, the general trend. The exceptions, yes, we will talk about. Okay. So exceptions
Yes,
are
sir.
there. So that's why if you see in the definition itself, okay, it is written generally. Why? Because there are exceptions. Clear?
Yes, sir.
So on the same account, electronegativity values decrease with the increase in atomic radii down the group. Now down the group, because atomic radii increase, that's why force of attraction decreases and electronegativity decreases. Same reason. These are few values on Pauling scale. So Pauling assigned fluorine as value 4. With respect to that, oxygen has 3.5, 3, lithium 1.9, etc. But you don't need to remember these values. No need to remember these values. You just need to remember the trends. Okay? That it will increase from left to right and decrease down the group. Yeah. Again, the same thing written differently. Electronegativity is inversely related to the metallic properties of element. Why? Because metallic properties are related to electropositivity. You know that most of the metals are on the left hand side highly electropositive. Okay? So lithium, sodium, potassium, rubidium, cesium, all these. Francium I don't write because that chemistry is not in your syllabus. That is a radioactive element. So these are, for example, here, and then I have beryllium, magnesium, calcium, strontium, barium. Okay? And then again, radon, I don't write, that is radioactive. So these are highly electropositive. These are metals, and metals are highly electropositive. And electropositivity is opposite of electronegativity. So here we are talking about electronegativity. So obviously, because metals are highly electropositive, electronegativity will be inversely proportional to metallic properties. Metallic properties are related to electropositivity. So you need to remember this point as well. Greater the electropositivity, greater the metallic character. Greater the metallic character, greater the electropositivity. So electropositivity is opposite of electronegativity. That's why electronegativity is inversely proportional to metallic properties also. This is the chart I was talking about. It is given in your NCERT book. And this is something you need to memorize. And if you can memorize this one, and if you can apply these concepts, this chapter and these type of questions are very easy. Apart from configuration questions, obviously, and other questions, you need to know other things, but related to trends, this chart is sufficient. So what this says, it says that ionization enthalpy increases from left to right and decreases. This one actually is opposite direction. Okay, increases, it means decreases down the group. Now we will consider in this chart only increase. So instead of saying that decreases down the group, we will say increases from bottom to top. Why? Because it will help you to understand it with vectors. So if you combine these two vectors, I'm talking in terms of mathematics, you will get a vector like this, resultant vector like this. Yeah. It means here it will be minimum. At this end, it will be maximum. Whatever property we are talking about ionization enthalpy. So ionization enthalpy will be minimum for the element in the periodic table on left bottom corner, and it will be maximum at right top corner.
Sir,
Yes.
so like, can we make any comparisons using this vector?
Yes, that's what I am doing here. Comparison I am doing, that if you are asked that which element is most electronegative, which one is most electropositive, which has maximum metallic character, which one has minimum non-metallic character, those type of questions you can do from here. Obviously, you need to apply the exceptions also. So first, we will be talking about generic trends. Then we will talk about there are few exceptions also. Yes, if those elements are asked, we will treat them as exception, and obviously there are reasons for those exceptions. Exception does not mean that without any reason that is exception. For example, it might be fully filled or half filled configuration. Due to that, there might be some exception, or might be that for most of the elements in the second period towards right side, there is no d orbital. So in many cases, we will see due to that there will be exception. In absence of d orbital, the excited electron cannot move to next orbital. That's why that will be exception. Moreover, in many cases, we will see that the exception will be due to the very small size of second period elements. Exceptionally small size means smaller than theoretical value. So exceptions are there. Otherwise, what you are saying, we are actually using this chart for comparative study. So for example, electronegativity vector is like this, and this one is electronegativity vector. The resultant will be again this one. So if it is resultant, here it is maximum, here it is minimum. Now suppose I talk about atomic radius or size. Size is something that it is increasing down the group and increasing from right to left. So in this case, the resultant vector will be like this. It is this here, it will be maximum here, minimum at the starting point. That's why fluorine has minimum radius, smallest one. Remember, in these trends, we are not talking about noble gases. Group 18 is excluded due to fully filled shell. Their properties are altogether different from other elements of the periodic table. So if you remember the metallic character trend, non-metallic will be opposite of this one. If you remember the electronegativity trend, electropositivity trend will be opposite of this one. Okay, so you don't need to remember everything. You just remember one so that there is no confusion. If you remember both electronegativity, electropositivity, there are greater chances of confusion. Remember only one, other one will be opposite. So today, after the class, that will be your homework, that you go through this chart. This is available in the notes. This is available in NCERT notebook also. And try to understand the trends in the periodic table. Then the next topic, periodicity of valence or oxidation states. More about it, we will be talking about in 8th chapter, redox reactions. Here, this is just reference. Valence or oxidation state in this chapter, these are used, interchangeably. But valence and oxidation states are different from each other. They are not same. The valence of representative elements is usually equal to the number of electrons in the outermost orbitals. Now, who will tell me what are representative elements? We talked about these earlier.
Sir, S and P block.
You had to raise the hand. Ye- Yes, Arjun.
Yes, sir. Sir, the elements were collectively of S and P block elements.
Fine. So S block and P block elements collectively are termed as representative elements. And in this case, it is equal to the valence is equal to the number of electrons present in the valence shell, or 8 minus the number of electrons present in valence shell. How do you to understand that? Suppose I am talking about lithium, okay, beryllium, boron, here carbon, nitrogen, oxygen. Now here the outermost shell, if you see the electron 1, here 2, because for lithium it's 3 electrons total, so it will be 2 comma 1. For beryllium 4 electrons, it will be 2 comma 2, 1, 2. Now here boron, carbon, here you can get the valence electrons by writing the configuration. Yeah, so I'm first writing atomic number 3, 4, 5, 6, 7, 8, 9. So you can write the configuration also. From there also you can get the valence electrons. It is easier in this case because there are very few electrons. Atomic number is very small. But otherwise, this is the method: 1s2, 2s1, 1s2, 2s2. So in 2 you have 1, in 2 you have 2, 1, 2. 1s2, 2s2, 2p, 1. So in 2 here you have 3. Similarly, here you have 4, 5, 6, 7 electrons. For example, for fluorine, it will be 1s2, 2s2, 2p6, 3s2, 3p5. So in valence, you have 7. 2 plus 5, 7. So valency is either whatever you have here, or if it is greater than 4, then 8 minus this one. 8 minus 5, 8 minus 6, 8 minus 7. 3, 2, 1. So that is what is the definition of valency. Nowadays, the term oxidation state is frequently used for valence, and it is actually different from valence, because valence is just one. So if we say it is either the number of electrons in the outermost shell or 8 minus number of electrons, it means it is fixed. But oxidation state is may not be fixed. Okay, it is something that is decided based on the compound in which that element is. So valence is something related to atom, standalone atom. Valence is something more related to standalone atom. But oxidation state is something when that atom is combined with some other atom and form the molecule. For example, if you have H2O and H2O2. In H2O, and more about it we will be talking about in redox chapter. In H2O, the valence of oxygen, that is oxidation state now I am talking about, is -2. However, in H2O2, it is -1. So same element, oxygen, has multiple oxidation states. Okay. May not be true for all the elements. For example, fluorine will always have -1 oxidation state, -1 valence, -1 oxidation state, same, and it will never change. But those are the rules we will be talking about in the redox chapter. Consider the two oxygen containing compounds OF2 and Na2. The order of electronegativity of three elements involved in these compounds is: fluorine is most electronegative, oxygen is less, and sodium is least electronegative. You know that, okay? Why? Because sodium and these lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then here you have sodium. I'm not considering neon here because neon, noble gas. When I compare fluorine and oxygen, fluorine is most electronegative, means oxygen is less electronegative. So oxygen is less electronegative than fluorine. And sodium, if you consider lithium and fluorine, if you consider lithium will be least electronegative because it is towards the left side. And again, moving down the group, electronegativity decreases. So sodium will be even less electronegative than lithium. So least, so sodium will be even less electronegative than oxygen. So comparative order will be sodium least electronegative, fluorine most electronegative. Whether you write it like this or you write like this, signs will change, meaning is same. These questions are very much common. Each of the atoms of fluorine with outer electronic configuration 2s2 2p5, fluorine is 9 atomic number, 1s2 2s2 2p6 2p5, sorry. So here you have 2s2 2p5 configuration. These share one electron with oxygen in OF2. Okay, I'm just trying to explain the difference. Okay, we are talking about valence and oxidation state. So if I'm considering OF2, oxygen is connected to two fluorines. It means this one fluorine shares one electron with oxygen in OF2 molecule. Being highest electronegative element, fluorine is given oxidation state -1. Fluorine will always have oxidation state -1. It cannot have any other oxidation state. Since there are two fluorine atoms in the molecule, oxygen with outer electronic configuration 2s2 2p4 shares two electrons with fluorine atoms and thereby exhibits oxidation state +2. Now this is change from what we have already talked about. Okay. So in H2O, I said that in H2O, hydrogen will have +1 oxidation state. So 2 into +1 will give you +2. And oxygen will have -2 oxidation state. So overall, +2 -2, 0. So H2O does not have any charge. So here oxygen had oxidation state -2. But I am talking about now OF2. In OF2 now the scene is entirely different. Chlorine has negative oxidation state. So if OF2 fluorine is negative, to neutralize the molecule, oxygen must have positive oxidation state. So remember the sum of all oxidation states of the elements in a molecule will be 0 because molecule does not have any charge. That's why. Any confusion? Let me know. So because fluorine has -1 oxidation state, say oxygen has X. Oxygen has X plus you have two fluorines and these two fluorines have -1 oxidation state and sum will be 0 because OF2 does not have any charge. So it means X will be +2, X -2 will be 0, X will be +2. It means oxygen's oxidation state in case of OF2 is +2, not -2. So oxidation states can be different for the same element in different molecules. But when we talk about valence, valence normally remains same. And valence, again, when we talk about valence, we don't talk about the molecules. But when we talk about oxidation state, we talk about the molecules also in a particular molecule. Similarly, in case of Na2O, all the alkali metals have been assigned the oxidation state +1 always. So all the alkali metals will have always, irrespective of in which compounds these are, except in free state. In free state, oxidation state of all elements is 0. Okay. So I'm not trying to confuse you, just for the sake of this chapter only. Okay. The alkali metals, lithium, sodium, potassium, rubidium, cesium, etc., strontium, oxidation state is always 1. The alkali metals always have oxidation state equals to +1. So if in Na2O, the sum of oxidation states will be 0 and sodium will have always +1. So in this case, 2 multiplied by +1 plus say oxygen has X will be 0. So X will be -2. In this case, it is normal. X is -2. So depending on the compound, oxidation state will be different. And how oxidation state is calculated? This is the simple method I told you. This is something I will explain, so I'm just skipping. These are just for reference, okay? You need to remember, but these type of questions will rarely be asked in this chapter. Most of these questions will be asked in Redox chapter, just for the reference only. Group 15 element P shows -3 oxidation state in pH3. Why? Because suppose P's oxidation state is X, then you have 3 hydrogens, 3 times +1. Hydrogen normally has oxidation state +1. Some will be 0, so X will be -3. So phosphorus can show oxidation state -3, but suppose I am talking about in PCl3. Okay, PCl3 0 oxidation state sum, say it is X plus 3 times. Chlorine has -1 oxidation state, 0, X equals to +3. So in PH3, it had -3 oxidation state. In PCl3, it has +3 oxidation state. Similarly, in PCl5, it has -5 oxidation, sorry, +5 oxidation state. So depending on which molecule we are talking about, oxidation state will be different. But there are certain rules which you need to remember. And if I go into more details, which have been given as examples in this chapter, you will get confused. So I'm just leaving it till Redox chapter. But if your teacher has done it in detail, then let me know. Normally teachers don't go into detail because it has to be covered in Redox chapter. Now the question. Using the periodic table, predict the formulas of compounds which might be found by the following pairs of elements: silicon and bromine. And this is something very, very close to what you have done in your 9th grade, 10th grade, previous grades. Yes, Bedi, yes.
Sir, I think it is SiBr4
Okay. Why do you think so? Just explain.
because silicon lies in the 14th group. So like there are 4 valence electrons. So and bromine lies in the 17th group. So there is 1 electron.
Okay, fine. Then next one, aluminum and sulfur. What will be the formula?
May I tell?
Okay. No, Kartikeya, yes.
The Al2S3.
Okay, why?
So because aluminum belongs to 13th group, so its valency would be 3, and sulfur belongs to 16th group, so its valency would be 2, because it has 6 electron in the outermost shell. So valency is 8 minus 6 equals to 2. So formula is Al2S3.
Fine, fine, good. So silicon has is group 14 element, so valence 4. Bromine is group 17 element, so valence 1. Okay, 8 minus 7 will be 1. Group 17 elements means 2, 8, 7. This will be the configuration. Outermost valence electron 7. It means valency will be 8 minus 7 equals to 1. Then you do cross assignment. Cross assignment means bromines valency will be assigned to silicons. Silicons will be assigned to bromine. Yeah. Number of atoms, not the valency, number of atoms. So bromine is 1, valency 1, silicon will be 1. Silicon's valency is 4, so bromine will be 4 atoms there to balance the charges. Charges will be balanced like this. Similarly, aluminum is group 13 element, so 3 valence. Group 16 elements, 8 minus 6, 2. Then you assign cross. So sulfur valency 2, 2 aluminum atoms, aluminum valency 3, 3 sulfur atoms, Al2S3. Next, are the oxidation state and covalency of aluminum in this particular compound same? Now remember, covalency is something in a molecule, okay, by how many ligands it is connected to. Covalency is by how many atoms it is connected to. So we are talking about aluminum, just see aluminum is connected to how many other atoms. Okay. Now this is slightly tricky one and slightly, I believe that it should have not been in this chapter, but because it is there, you have to do. Understand the difference here. Covalency is, in this case, aluminum is attached to how many other atoms. Okay. These atoms might be of some other molecules, for example, atoms of H2O. So if you consider this one, in this case, aluminum is attached to 1 chlorine and 5 H2. So its covalence is 6. Covalence is 6. Yeah. Remember, H2O is a neutral molecule, but if you are considering only chloride, this one chloride in this form, for example, NaCl, or if I consider only AlCl3, then in that case, these will be broken down into like this. Al3 plus 3Cl minus. Okay. NaCl has Na plus and Cl minus. Means chlorine has one negative charge. H2O is neutral. Why I'm talking about? Because now I'm moving to oxidation state. So to calculate the oxidation state, sum of all oxidation state should be equal to overall charge. So when I considered, say, OF2, I summed up, added up all the oxidation states, and I said that the sum should be equal to 0. Why? Because there was no charge. That's why the charge was 0, so equal to 0. But here, the charge on this one is plus 2. It means sum of all oxidation states should be equal to plus 2. So oxidation state of aluminum, we have to calculate, say it is X, plus oxidation state of chlorine, minus 1, plus oxidation state of H2, overall it is neutral, so it is 0, 5 times 0. This whole will be equal to plus 2 because we have plus 2 charge for this. And so from here you will get X equals to, this part is 0 anyway, this minus 1 when goes on right side becomes plus 1, 2 plus 1, 3. So it means oxidation state is plus 3. However, covalence is 6. So both are not same. Covalence is to how many other atoms it is connected to. Aluminum is connected to. Oxidation state is that how many electrons are being transferred, how many electrons are taking part while reaction is happening. So that's the difference. Yes, someone was saying something. Okay. So this is what you need to understand in this chapter. But when we consider this one in redox chapter, it will be more clear.
Sir,
Yes.
sir, I did not get this properly. Can you please tell again?
Which property? Oxidation state or covalence?
So the
Sir,
covalency one.
yes, sir.
Covalence one is that if you write this formula, it says that aluminium is attached to 1 chlorine and 5 H2O. H2O whole 5 means there are 5 H2O which are connected to aluminium, and there is 1 chlorine which is connected to aluminium. So it means total 6, 1 chlorine and 5 water molecules are connected to aluminium. That will decide the covalence. 6 attached, so covalence will be 6. In
Okay.
simple terms, covalence is how many atoms are connected to the central metal atom. Central metal atom here is aluminium. Now, moreover, this compound actually we will be talking about in 12th grade, coordination compounds. There is whole chapter on that, okay, complete chapter. So that's why I'm saying for now, this much is sufficient. If I explain, there is something I can explain for 4 hours, 5 hours, that will be 12th grade, not 11th grade. So in 11th grade, this chapter, this much is sufficient. That covalences with how many other elements it is connected to, and oxidation state is actually how many electrons are getting transferred during the reaction. That's how you calculate the oxidation state here. So the oxidation state and covalence are not same. So first question was, are the oxidation state and covalence of this one same? Answer is no. The oxidation state is +3, covalence is 6. Now the anomalous properties of second period elements. Many questions will appear from here. Anomalous properties. Okay, these are actually the exceptions, and there are reasons for exception. So when we talk about the second period, this is the second period. The anomalous behavior is attributed to means it is because of their small size, large charge to radius ratio, and high electronegativity of the elements. The one point which is not written here, and more about that we will be talking about in chemical bonding chapter also. That is something, the d block is not present, d orbital is not present, d subshell is not present in second period, because for second period n is equal to 2, L will be 0 and 1, means S and P only. D is not there. So if D is not present, even the excited electron, if it gets excited, cannot occupy D. D is not present at all. That's why the properties of second period are different. Why? Because they have very small size. When we see a small size, is smaller than theoretical values. They have large charge by radius ratio. Why charge by radius ratio is important? This is actually charge by radius ratio which decides the properties are similar or not. So in periodic table, when we say that we have clubbed the elements in the same group because they have similar properties. Remember, all the elements in the same group, for example, group 2 will have similar properties, group 3 elements will have similar properties. Okay? All elements in group 15 will have similar properties. But what is the underlying reason? The underlying reason is that their charge by radius ratio is same. Sometimes this question is asked. Okay? The same periodic properties, okay? The same properties of the elements, the chemical and physical properties of the elements are attributed to what? Are attributed to their charge by radius ratio. That's what you need to remember, how much charge is there and how much radius is there. So 4 points I am talking about which decide the difference in properties, specifically second shell or second period. A small size, large charge by radius ratio, comparatively high electronegativity, and absence of d orbital. Okay. So absence of d orbital is written here basically. So this is actually absence of d orbital. It says, in addition, the first member of the group, which one? Barium, boron, carbon, nitrogen. Of this group, nitrogen is first element. Of this group, oxygen is first element. Okay. So first element means we are talking about second period normally. So the first member of each group means second period has only 4 valence orbitals, 2s, 2p. 4 valence orbital means 2s, 2p, s, and 2p will be like this. So there are total 4 orbitals. However, the other ones, okay, the second member, for example, second members, these have 9 valence orbitals. So for example, I consider magnesium. Magnesium atomic number 12, 1s2, 2s2, 2p6, 3s2, like this one. So here, third shell started. Till fluorine or neon, say fluorine 9, it was 1s2, 2s2, 2p5. That's it. 9 electron. Means there is no d orbital. In second shell, the valence shell is 2, and n equals to 2 means L equals to 0 and 1 means S and P. D is not there. But if I consider sodium or magnesium, say magnesium, the electron is in third shell. And if it is third shell, n equals to 2, L will be 0, 1, 2, means S, P, D. Now D subshell is there. So electron can get excited to D subshell. So that's what is written here. So the second member of the groups have 9 valence orbitals. So the electrons can get excited to higher level, and the higher excitement, number of excitement possible, higher number of oxidation states possible, higher number of compounds possible. Okay, more about it in chemical bonding. Just reference here. As a consequence of this, the maximum covalency of the first member of each group is 4 only. Why? Because there can be only 4 orbitals which can take part in bonding. Whereas the other members of group can expand their valence shell to accommodate more than 4 pairs of electrons. That is, aluminium forms AlF6 3-. So this is just an example. You need to understand why, because aluminium will have 1s2, 2s2, 2p6, 3s2, 3p1. So valence shell is like 4. Okay. So there is possibility here in this case that 3s2, that because it is third shell, there will be D subshell also present in there. So in that case, more than 4 electrons can be paired. Now you can say that why, how can it be possible? In aluminum, we have only these 2 electrons. So maximum possibility is that this electron will get, this one electron will get excited to p. But these type of compounds, as I told you, these are complex compounds, coordination compounds. More about it we will be talking about in 12th grade. These are actually coordinate bonds. These form coordinate bonds, and that's why the name coordination compounds. Okay, coordination compounds because these form coordinate compounds. And how these compounds are formed? Actually, fluorine provides its both of the electrons to these empty orbitals. So how it works? I'm just drawing it again. I'm not going into much details, and your teacher will not go into much details unless you are in DPS. Yeah. So what happens that in coordination compounds, these orbitals do not form bond. These do not take part in bonding. Rather, what happens that you have 6 fluorines, fluorine, 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 and fluorine has 7 electrons. Each fluorine has 7 electrons. Each fluorine gives both of its electrons to 6 empty orbitals. That's how 6 fluorines are there. Why it can happen? It can happen because the aluminum has d orbitals. Why it cannot happen with boron? Because boron, the maximum highest shell is 2, and 2 cannot have d orbit. Is that clear? What is the limitation
Yes.
with second period element? That is the limitation. Okay. So that is the limitation. We treat it as anomalous behavior because it is something different from other elements of the same group. That's why we say it is anomalous behavior, but there is reason, as I explained the reason here. Okay. Furthermore, the first member of p block elements displays greater ability to form p pi multiple bonds to itself. For example, carbon carbon can have double bond, carbon carbon can have triple bond, nitrogen can have double and triple bond. And to the other second period elements, for example, carbon can have with oxygen also double bond, carbon can have with nitrogen also double bond, with nitrogen it can have triple bond, nitrogen can have double bond with oxygen. Means what I am talking about, that the elements which are here, these have greater tendency to form multiple bonds. So first bond is called sigma bond always. The other bonds, second and third, are called pi bonds. So you need to just remember the names also. So first bond formed is sigma bond. These two are called pi bonds. Now these pi bonds are formed by p orbitals. How these are formed by p orbitals, we will be talking about in chemical bonding. That's why these are known as p pi multiple